Good morning, or afternoon, or evening, depending on where you are, and welcome to Pathfinder Rules course. I'm Dan, and you can reach me at my email address here. You can find it on the Perimeter Institute website as well. In addition, I will be joining the Zoom meetings early and staying a few minutes after the class ends in case you have any questions. So those are three ways you can reach me if you do want to discuss anything from the course further. So I am a Perimeter Scholars International Fellow at the Perimeter Institute, which means I spend the majority of my time teaching in the master's program at the Perimeter Institute. And you'll be receiving some information shortly about a question and answer session we'll be hosting later regarding the Perimeter Scholars International Program, if you're interested. So a bit about me. It feels like a very long time ago, and also very far away. So that is in March and 5 kilometers from here. I used to run the Perimeter Institute Orchestra, so I played the trumpet. You can see me here, as well as doing some organizing and arranging music. So that was one of my hobbies. Previously, more recently, I spend my free time taking care of my son here, who's, you can see, he'll be turning three in a few days. That's just a little bit about me. Also with us today will be assisting me throughout the course is Remy. You can see him over there. He's waving. So he is a current PSI student. I don't know, Remy, if you'd like to say anything.
Hi, everyone. Yeah, I'm glad to be here. If you have any questions about physics, about life, don't hesitate and listen to Dan. There's a lot of things to teach you. Okay, we'll talk soon.
Thanks, Remy. Okay, so the way this class is going to run is it'll be a mix of lectures and tutorials. So the lecture section of the class, I'll primarily be using the Zoom whiteboard. This is probably the only time I'll be using slides. This is very introduction to this first class. And in every class, there will be one or more tutorials where I'll divide you up into breakout rooms to discuss some physics problems, to work collaboratively together. There's a really effective way to understand the material. So we'll be spending approximately half of each class in lecture and half in tutorial. And often there will be several transitions. Today we'll begin with some lecture, and we'll go to breakout rooms, and with lecture. Other classes, there might be several transitions back and forth. So the lecture part of the class is recorded. Once you're in a breakout room, nothing will be recorded. So anything you say there it's not going to be part of the recording. So teaching virtually via Zoom is new to me. I imagine it's new to a number of you. Maybe this is the first Zoom, or maybe you had one or two Zoom courses before. But I just wanted to briefly say a few words about running a virtual classroom effectively. So some of the, I think most or all of you were at the welcome meeting last week, but just to recap a few things. So one is if you have questions, you can use the raise hand button. If you, for any reason, want to ask your question anonymously, feel free to send your question via chat to Remy, who will read it out to me. And please do ask questions as they come up. The more interactive this can be, the better things will be for both of us. So please stop me and ask questions as they come up. If any of you have suggestions for things that I could do or you or your classmates can do to make this more effective, I'd be happy to hear any suggestions you may have about running classroom virtually. Anyone would like to comment now, or you can send me comments later as well. Okay. So during the other half of class, we will go into breakout rooms. We'll divide you into rooms with three or four of you in each room. And the idea behind these breakout rooms is to simulate virtually Blackboard discussion. So there will be problems that I will load into the Google Drive. They're there already. And the idea is that you can discuss these problems with your classmates. In the welcome meeting, we saw that the Zoom whiteboard is one way that you can share mathematical expressions. There are other options on that if you prefer to use something else. There's a document in the Google Drive that explains some of the other options. Remy and I will be jumping around between the various breakout rooms to assist you if any questions come up, joining your discussions. If you would like, if something, don't happen to be there when a question does arise, you feel, please use the help button. That will send a message to me. If I'm in the middle of a discussion, I can send a message to Remy, who will be there to assist you as soon as possible. And so again, the idea is really to have a discussion to try to understand these problems. Before we go to the breakout room, I will send you another link to the Google Drive, but it's the same one that Giuseppe sent you earlier. And again, I'd be happy to hear any suggestions you have now or later regarding how to make these discussions more effective. Are there any comments or questions before we begin? Okay, so our topic for this course is path integrals. And the path integral is an alternative formulation of quantum mechanics. It looks mathematically and formally very different from the formulations of quantum mechanics you have already encountered, but it's entirely equivalent. It makes exactly the same physical predictions. And so it has many applications. So first of all, it's interesting just because it's a very, very different formulation and in terms of paths, which gives it, so one reason path integrals are interesting is the connection with classical physics is much more closely connected to classical physics than formulation in terms of a wave function or using the Schrodinger equation, etc. In classical physics, one of the most commonly studied quantities or objects, mathematical objects, is a path. So one of the first things you might study in your first classical mechanics course is a trajectory. So for instance, you might be interested in what happens if you throw a ball, and you can compute the trajectory of that ball. Now, in the usual formulations of quantum mechanics, that's not really a question you can ask. What is the quantum mechanical trajectory of the ball? The uncertainty principle says the position and momentum are uncertain, so it's not really a question that can easily be asked in terms of a wave function. The path integral formulation isn't formulated entirely in terms of paths. So that's the connection with classical physics is much more direct than in other formulations of quantum mechanics. So that's one interesting aspect of path integrals. It has another of several other important applications and advantages over other formulations of quantum mechanics. So one such advantage that we'll discuss later in the course is in quantum mechanics, very few things can be computed exactly. So often we compute things as a perturbation series in some small parameter. And well, most often those perturbation series have a finite radius of convergence or even zero radius of convergence. So they don't capture all the physics, and some physics is missed when you do perturbative calculations. For example, quantum tunneling in a naive perturbation series is not something you can compute, and there are nice ways to use path integrals to compute non-perturbative effects like tunneling or splitting of ground state energies. In addition, path integrals can have other applications to areas like quantum field theory, because multi-dimensional integrals are often easier to solve than high-dimensional differential equations, which are generally very difficult to solve, and quantum field theory can be thought of as an infinite dimensional limit of quantum mechanics. So there are a number of practical and theoretical reasons to be interested in path integrals, which we'll explore a number of throughout this course. So in today's lecture, I'd like to motivate the path integral, and later classes we'll see how it's equivalent to other formulations of quantum mechanics and some of its applications.
Dan, I think there might be a question.
Okay. Yes.
Can I just talk?
Of course. Yes, please go ahead.
I wanted to know if it's possible to find a path for the double slit experiment with path integrals, because I've heard about Bohmian mechanics, but I guess that's not part of the topic, but this is also an alternative description of quantum mechanics.
Yes, the double slit experiment is, in a sense, the simplest example of a path integral. Really, there's sense of just two paths that contribute.
Mhm.
That's exactly the direction I was about to go, is that in a sense, we can think about the path integral as just a limit of the double slit experiment where we add more slits and more screens.
Okay.
But the path, that's Feynman, building on work of Dirac and Wiener, was really thinking about the double slit experiment when he came up with the path integral formulation.
Okay,
So that's
but
exactly.
does that mean that the path integrals would be for both paths? Because what I've learned from experimental physics is that they say we don't know through which slit the particle would go. So would we have two paths or would we have one path?
We have two paths.
Okay.
So yes. So in general, in the
Yeah.
path, it's a path integral. So in the double slit, that integral becomes a sum. So there's only two paths to contribute. But generally in the path integral, we're talking about infinitely many paths contributing to every process.
Okay, thank you.
Yeah, thank you for the question. Okay. So building on that. So the double slit experiment. So we start with a particle somewhere over here. And there are two small slits. So we send the particle at the screen, and there are only two possible paths it can take. It can go in the upper slit or the lower slit, and then it's measured somewhere on the screen. And what's observed, if you set up this experiment, is an interference pattern. So the amplitude for the particle to go from its initial position to its final position where it's measured is equal to the amplitude for the particle to travel on path 1 plus the amplitude for the particle to go on path 2. And so these two paths can interfere constructively or destructively, and this leads to the interference pattern that's observed on the screen. And so, as I was alluding to when I answered Sarah's question, and let me just go into a bit more detail. One way to think about where the path integral comes from, to imagine the same experiment where we've got some screen where we're measuring the final position of the particle, and the particle starts over here. But if we add more slits and more screens, what happens is there are more than two paths that the particle could take. So if I have a screen here with 3 slits, particle can go through any of the 3 slits. And if I put a second screen here with 3 more slits, from any of those first slits, you can go to any of the slits in the second screen, and so on. And if I add more screens, the number of paths increases. But the same reasoning as before holds. We can write the amplitude for the particle to go from its initial position to its final position as the sum over all paths gamma of the amplitude for each of the paths. And so this K here is what's known as the propagator. There's a question from Pavlo.
Yes, thank you. What do we mean by amplitude of the path?
We are associating, so what I mean there is we're associating a complex number with each path. So one thing we're going to discuss later in this class is which complex number should we associate with each path. So this here is a complex number associated with each path.
Okay, thank you.
Okay. And so the propagator is a function of the final position of the particle, which I'll call Q, F, the final time of the particle, which is measured on the screen, the initial position and initial time of the particle. And so this is something we can compute using the formulations of quantum mechanics we already know. And if I was going to compute this amplitude for a particle to go from some initial position and some initial time to a final position at a final time, I could write that as, so the particle is starting out at some position Qi, ending at a position Qf, and we need to time evolve it for some time e to the I h t over h bar, where t is equal to tf minus ti. So this here is the time evolution operator. So here we have an expression, at least a sketch of an expression for how to compute propagator, which is something we could compute using formulations of quantum mechanics we already know, using path integrals. So what we need in order to flesh out this construction is, well, we need to understand what complex number we should associate with each path. That's really the key question that allows us to turn this idea into a formalism that we can use to do physics. And so today we're going to see that we can actually put some fairly strong constraints on what this functional A of gamma should be based on a few general considerations. And in the next class on Thursday, we will see that in fact that we were forced to make that choice.
Dan, excuse me. I think we have a question, Pablo.
Yes, Pablo. Yes, here H is the Hamiltonian. Okay, Sartat has a question about this equation here. So K here, the propagator, is defined to be the amplitude for the particle to go from the initial position at the initial time, the final position at the final time. And so this expression on the right-hand side is that amplitude. So here, the particle is starting out at some position Qi, and here I put in the time evolution operator, assuming that H is time independent. And so we're evolving it for some time Tf minus Ti, and then projecting it onto the state Qf. So you can take this to be the definition of of the propagator. And what I've argued, based on the generalization of the ideas behind the double slit experiment, is that we can compute this propagator in another way by summing over paths. So that's the idea we're going to be exploring throughout this course. Is that we can compute this expression in a different way. Okay, so let's go back to here. So here I've drawn a picture of the trajectory of the particle through space. So this is a trajectory where, looking at the particle, there's no time on this diagram, just space. So let's draw a new diagram where we integrate the space-time history of the particle. So here I'm going to sketch on the vertical axis the position, and on the horizontal axis time. And so we're assuming that the particle starts off at some initial position qi, which I'll give another name q0. And it ends at some final position qf, which I'll give another name as qn. And so if we put a bunch of slits and a bunch of screens, and suppose we have n screens, then after a time delta t, the particle will have some position q1. And if we make the slits infinitely small and infinitesimally close to each other, then there's essentially no screen there. So the position q1 could be anything. And if we have n screens, then at each of n times, which we'll take to be equally spaced. So if we space the slits equally so that the particle goes through the slits after a time, goes through each screen after a time delta t, then at time ti plus delta t, the particle can have any position q1. At the time ti plus 2 delta t, the particle can have any position q2, and so on. So the sum over paths is the integral over dq1, dq2, dq, n minus 1. That's what the sum over paths means in this limit, and we can take the limit n goes to infinity, and have infinitely many screens, so that this time delta t goes to 0. So we can approximate any path as a sequence of, and there's a question I'll get to in just a second, as a sequence of straight lines of infinitesimal length. And so there's a question, are there any restrictions on the nature of the path such that the path must be continuous? So there are no restrictions on the nature of the path. The particle can go from any position q1 to any other position q2, which means, well, it will be continuous, but it won't be differentiable. So a typical path, if Q1 and Q2 are different and we take the limit delta t goes to 0, then that's not going to be a differentiable function. It will be continuous. So, so there's another question. We're considering paths. Are we considering paths in the topological sense? No, we're considering. So our paths. Each path is a function. Each path, in this continuous limit, each path is a function q of t. So in this limit, so if we discretize it, we're specifying where the particle is at just some finite set of intermediate times. If we take this continuum limit, then we're specifying the particle at each time t in between the initial time and the final time. So a path is a function, not necessarily a differentiable function, but it's a function. We did, so there's another question. We did take time when we initially took time and space to be discrete, but we're taking the continuum limit. So first we're adding in screens with a finite number of slits, and we're taking the limit where the number of slits goes to infinity, the number of screens goes to infinity, and the spacing between everything goes to 0. We're discretizing first and then going back to the continuum. Okay. All right, so if we want to describe tunneling, we can use continuous paths. We'll see next week. There are our technique for describing tunneling is going to involve essentially treating our time as a complex variable. So that's a big topic we'll get into next week. Okay. So that's what the sum over paths means. And in order to make our formalism complete, we need to figure out what this functional A of gamma is. And so there are two expectations we have, and as we'll see in the tutorial, these expectations actually greatly constrain what this functional A of gamma should be. So one, expect there to be a factorization property. So if I have path, I should be able to divide it in parts and consider it as one path followed by another. So here I have some path gamma 1, which goes from here to here, and a second path gamma 2. I could consider those as a single path gamma 1, 2. And I expect this functional, if I'm computing this complex number I'm associating with each path, the complex number associated with the whole path should be just the product of the complex number associated with each half of the path. And that, as you'll see in the tutorial, tells us that the propagator should obey a composition property. So K of QF, TF, QI, TI equal to the integral dy of K, QF, TF, y times the intermediate time times K of y. That's the intermediate time, QI, TI. So this equation says that if the particle goes from QI to QF. In the middle, it's got to be somewhere. In between, it's got to be somewhere, some position Y at the time TI. And if we integrate over those Ys, then we can break the path up into two that way. So these two are related. So we should be able to break our paths up. That's something we expect. And that will put some constraints on what this functional A should be. Our second expectation so this last formula. Okay, so this says, so here's K of QF TF QI TI, this is a T, is the integral dy of K of QF TF, this is a Y, and the T intermediate, T sub int, and this is a K, Y, T sub int, QI, and TI. Is that clear, Kofi? Okay, thank you. So our second expectation is we expect that there is a classical limit. So classical limit you can think of in two ways. So mathematically, we can think about it as the limit h bar goes to 0. If you don't like that, because h bar is a physical parameter, we can also think about it as the limit where the action S is much greater than h bar. So in this limit, if h bar is small compared to the action of classical path, then we expect we're in the limit where classical mechanics is a good approximation. So in this limit, we expect that classical paths are most important. They should in some sense be the most important. They should provide a good approximation to the amplitude in a sense that we will discuss more. And so here, and for most of this course, we're going to consider a simple but very important example where we have we're considering a point particle with action 1/2 m q dot squared of t minus v of q of t. So this is the action for a particle moving in a potential. It's just a point particle moving in a potential. It's the example you've studied in your classical mechanics, your first classical mechanics course. Here I'm formulating things in terms of an action. And so one way to get the classical path from the action is the classical path is the path that extremizes the action. So the variation of the action, if we do a small variation of path, is 0. And that, in this case, gives us the equation of motion for a point particle moving in potential v. And so here v prime is the derivative of v with respect to q. Okay, so these two expectations we'll see in the tutorial are actually very constraining for what this this choice of A should be. Either one alone will not be enough to say something, well, to determine A, this functional A, but together they'll give us lots of information about how to construct the path integral. So we're going to go into breakout rooms now. I will, in the chat, send you the link to the Google Drive again, in case you don't have that readily available. So in the Google Drive, in the Lecture 1 folder, you will find some tutorial problems. Also, the math document is in the main folder, in case you have any issues sharing math over Zoom. So I will divide you into breakout rooms now, and we will. So I'll leave you in the breakout rooms for about half an hour, and then we'll come back to the main room for a brief discussion for the last 15 minutes of the course of today's class. Okay, I think everyone is back now. So just want to briefly discuss some of the key results from the tutorial. So one is, so in the first problem, we should have shown that the composition property that we expect, that we can break up paths into sequences of paths, places some constraints on what the functional A should be, but it's not enough to uniquely determine it. There's some unknown constants we have. And in the second problem, so I want to discuss in a bit more detail. We're comparing two different integrals. And so if we want to approximate an expression given by an integral of this form, in the first case, if f is a real function, then the most important contributions to this integral are given by the regions where f is smallest. So in other words, on the regions where f prime is 0, with f double prime positive are the most important contributions to this integral. So the regions near where near the minima. It's possible there's one minima or several minima. In this case, in this other case, the integrand is a complex number with magnitude 1. So every point is, in a sense, equally important. Nevertheless, some regions are more important than others. Because if f prime of x equals 0, then locally, the complex numbers all have the same angle, the same phase, so that they will interfere constructively. So those regions are more important, regions near where f prime is 0, because we'll get constructive interference, versus regions where, if say, if f prime is finite and big, then e to the I f of x is going to be changing phase rapidly, and we'll get destructive interference as the complex number points in different directions in the plane. So in both cases, the regions where f prime are 0 are potentially important, but in the case where we have the minus sign instead of the I, we need to put an extra condition. So only some of the solutions with f prime of 0 are important. In this case, all of them are important over here. So if we want the classical trajectories have delta s equals 0. So the variation, that's like the derivative of s equal to 0. So if we have an I, then all classical solutions will be important. Whereas if we had a minus sign, only some of them would be. So we want the classical, all of the classical solutions to be the important contributions, then we should have an I there. So that essentially fixes our expression for the propagator to be integral over paths, so of e to the I times the action of that path over h bar. So this is the expression we essentially uniquely determined based on just, almost uniquely determined based on just these two considerations. And so we see here that all paths contribute with equal weight. So the classical path, so for a ball, if I throw a ball, the classical path would be a parabolic path. That path contributes with exactly the same weight as a path where the ball goes in 3 circles around my head and then ends up in the same spot. So those two paths are equally important in the sense that those two paths contribute the same to the propagator, but the classical path interferes constructively with the paths that are nearby. Dario has a question.
Yeah, sorry, just what is that first symbol after the integral?
So this is a script D. So this here, this measure is a shorthand notation for the integral dq 1 dqn in the limit that n goes to infinity. So we're integrating here over all functions dq of t, which is the limit n goes to infinity of the integral we had before.
And you called that a measure? Is it a measure?
It's a measure, yes.
Okay.
Okay, I think that's this same question that was in the chat. Yes.
I think we had one more question. Someone raised.
Was there another question?
Yes. This propagator is just for the double slit problem, or it's for like a general problem with different paths?
This is for a general problem. This expression here that in the box is the expression, path integral expression for the propagator. It's equal to this expression here, which was, well, actually the expression I wrote in the box is more general than this one. Here I assumed that it was Hamiltonian was time independent. I made no such assumption, path integral expression. So it's equal to this is the amplitude for a particle to go from some initial position to some final position in a time.
Okay, thank you.
Okay. So
And there's one more question in the chat.
one more question, yes. Should we read that as Lebesgue integral? Yes, I Yes, I believe so. Okay. So okay, the correct classical limit okay, so the correct classical limit means that the classical paths are more important, and but in a very specific sense. So classical paths are more important because not because individually, just as an isolated path, they're any more important than other paths. They're not. They're exactly as important as any other path, regardless of how wildly improbable or wildly aclassical it is. Classical paths are more important because they interfere constructively with the nearby paths. So a more technically correct way to say it is that the regions near classical paths in path space are more important than other regions. The classical path itself is no more important than any other path, but the region around it is more important. Okay. Yeah, so I was essentially where I was going before. So if we have two nearby paths, Q of t, Q prime of t, and we want to look at these, just considering those two paths alone, it can be shown that this is approximately e to the I s of q, 1 plus an exponential I over h bar. It's the integral then on the next line, integral dt of eta times the variation of s dq, where eta is q prime of t minus q of t. That can be shown. So if the classical paths have ds dq equal to 0. So for classical paths, we've got the exponential of 0, and these two paths will interfere constructively. If q is not a classical path, then ds dq will not be 0. And as h bar goes to 0, we've got e to the I times something large, which in general will could be close to pi. So there may be destructive interference if it's not a classical path. But if it's a classical path, then this ds is 0. So we will have constructive interference. So and h bar goes to 0. We get constructive interference near classical path. So that's the sense in which the classical paths are more important. Okay, so from here, there are many possible routes we could go. We could discuss the connection between this formalism and other formalisms, connections to physical physics, perturbation theory, non-perturbative physics. And since this is a path integral course, the only reasonable way to proceed forward is to take all possible paths. So we'll discuss a bunch of those topics for the next few courses. So I will stick around for questions for several more minutes, but we're out of time for today. So I'll see you on Thursday. Thank you.
Thank you, Dan.
Thank you. Pavlo.
Yeah, what is epsilon from T?
Epsilon, oh, where?
You write variation S or divide variation epsilon of T.
Oh, this
or
is supposed to be
what is
Q. That's supposed to be Q.
Q, okay.
I apologize for the unclear writing. Please stop me if anything's unclear.
And then one more question, why we can write this equation or near equation?
Oh, so what you would want to do to the intermediate steps, which are, we would essentially want to do a Taylor expansion. So S of Q prime of T is, so if Q and Q prime are close, so it's S of Q. That's essentially the 0th order term in the Taylor expansion. The next order term in the Taylor expansion is the integral dt eta of T ds of Q d Q of T, and there'd be higher order terms. And the way to understand this term is, so here we're taking a derivative of S with respect to the function Q. We can think about what we would do after if we discretize it. So if we discretize it, then S would just be a function of many variables. So we'd take the derivative of S with the, so if we're doing a multi-dimensional Taylor expansion, we take a derivative of S with each of the variables, multiply by that variable, and then sum over those variables. So that's what we're doing here, but it's we have continuously many variables, so it's an integral instead of a sum. And this symbol means it's a functional derivative instead of a partial derivative. It's in spirit, essentially exactly the same thing. Just the Taylor.
Okay, thank you.
Two more questions, hands up. I don't. Esha, am I saying your name right?
Yeah, it's Isha. Yeah. So, like, in the when we wrote this integral expression, the second one.
This line here.
Yeah, the e to the this one. Yeah.
Okay. Yes.
So how does this like make more clear that there is constructive interference between near the classical paths?
So classical path means that this is 0.
Yeah.
So if this is 0, then we have, so if this is 0, then we have
Okay,
one,
so you want to say that it's 1. Okay.
1 plus e to the I times 0. So that 1
Yeah, okay.
interferes constructively.
Yeah, okay. Thank you.
Thank you.
I think we have a question from Dario.
Yeah, so you've showed that this particular form gives rise to the correct classical limit.
Yes.
But you also ask what other forms give rise to the correct classical limit in the question preceding that.
Yes.
So you said this pretty much uniquely determines the form. Now, I kind of follow what you've done here with my limited understanding of variational calculus. But if we wanted to show that this was the only form or that it was essentially unique in some way, how might we go about doing that?
Okay, so what we can imagine that would give the other forms that would give the correct classical limit would be, let me go back to this. So we want an I here so that we're only picking out the, so we're picking out all of the classical paths. But just if we only consider that we want the correct classical limit, we could imagine having something like e to the I s squared.
Right, okay.
Something like that. That would have the same classical limits, the same, so the paths with delta s equals 0 would also be important for an integral like that. The problem is that if we had e to the is squared, that would not have the correct composition property or factorization property.
Right,
So
okay.
if we just want correct classical limit, there's lots of possibilities. If we just want correct composition property, there's lots of possibilities. Together, they're fairly constraining.
But we could, for instance, have minus I, right?
We could, yes.
Right.
So it's not, these considerations are restrictive and suggestive, but it's not a derivation. We'll sketch one next time to see why this is exactly the same as ordinary formulations of quantum mechanics. Okay. So I'm being told you need to go to the next course very shortly. So I think we'll wrap up. Maybe I can time for one more question if anyone else has one. If questions do come up before next time, I will join the next meeting early, and also feel free to email me.